Hello, everyone. My name is Toso, and I will present the paper Fixing Implicit Derivative, Trust-Region-Based Learning of Continuous Energy Function that was already presented at NeurIPS 2019. So in computer vision, In computer vision, many tasks can be described as energy minimization problems, where we have some sort of data, and we feed it to an energy function that depends on some hyperparameters. We minimize the energy and get some reconstruction. And the practical examples we consider in our work are human pose estimation from multiple cameras and the fusion of multiple visual trackers. So let's say we have one of these energy minimization problems, and we want to estimate how accurate it is. We might introduce some loss function in which we compare ground truth and reconstruction. But the problem is that we are likely to see that whatever minimizes the energy will not necessarily minimize the loss. And this is because when we build our energy, we do some approximations, plus our data can be noisy. So what we'd like to do is to learn the ideal configuration of hyperparameters so that when we minimize the energy, we also minimize the loss. And to do this, we can take our energy minimization problem and insert it into a bigger optimization over the hyperparameter space. And this gives rise to a nested optimization problem that is not always possible to solve because, as was already mentioned today, differentiating through an argmin, it's not always easy, not always possible. So a common solution is to use implicit differentiation. And the idea of implicit differentiation is that as long as we can find a way to compute the Hessian and Jacobian of the energy at the minimum, regardless of how it was actually obtained, we can get the gradient of the reconstruction with respect to the hyperparameters. So this is a very interesting result, very useful, and it can be proven that if our energy is strongly convex, let's say if it's quadratic, we can actually guarantee that hyperparameter optimization will converge. Sadly, in our work, we show that this is not the case if the minimum of the energy is better approximated with something that is as a higher order than quadratic. And in this case, what is likely to happen is that the determinant of the Hessian will become increasingly small, resulting either in an ill-defined inverse Hessian or generally in an Hessian increasingly large that will result in exploding gradients. And as a solution, we propose a different framework we're calling Wibergian Learning. And the idea is, first thing, we approximate the energy minimum with a functional of the hyperparameters. The idea is that if the energy is well-behaved enough, for the purpose of computing the gradient, we can locally approximate it with something that could admit a closed-form solution. And this is what gives the name to our approach, because it's reminiscent of how in Wiberg optimization, one divides the parameters into classes, keep one constant and see that with respect to the other parameters, it's possible to find a closed-form solution and then replace these latter parameters with their analytical form, meaning that we have an optimization in a lower dimensionality space. The second step is showing how implicit differentiation can be derived from the Newton's method. The idea here is that if we start with some energy function that should work with implicit differentiation, let's say strongly convex function close to the minimum, and we fix the hyperparameters, if we start close enough to the minimum, what we can do is we can locally approximate the function with a second-order Taylor expansion, obtain from it the Newton's update rule, and this will move us towards the minimum. Once we are at the minimum, this Newton update rule will become a fixed point equation. We then ask ourselves, well, what happens now if we change slightly the hyperparameters? If the perturbation is small enough, the energy will change its shape. It will have a new minimum, but this new minimum will be still close enough to the old one that, starting from the old minimum, a single iteration of the Newton's method will push us towards the new one, and we can then reevaluate the fixed point equation in this new minimum. If we then consider the limit of the perturbation going to zero, This will give us the same gradient update of implicit differentiation. And the idea is that Newton's method has the same weakness, same instabilities of implicit differentiation, because its update step depends on the same inverse Hessian. So we wondered what would happen if we started instead with a different optimizer, and we chose the trust region method that, as mentioned in the previous presentations, adds a small diagonal term to the Hessian before inverting it. And the idea is that we then are solving the same quadratic programs of Newton's method, but with the upper constraint on the size of the update step. And this means that when we are dealing with energies that are strongly convex near the minimum, we have the same convergence properties of Newton's method. But when Newton's method starts to fail, we have better performances because our update steps are dumped. And if we then take Newton's method, trust region method, and feed it through the same process we use to derive implicit differentiation from Newton's method, we obtain a new gradient rule that is very similar to the implicit differentiation one, but adds a diagonal identity term to the Hessian before inverting it. So summing up before moving to the experiments, the algorithm we propose has weaker requirements than implicit differentiation because it's enough for the energy to be smooth near its minimum instead of strongly convex. Both our method and implicit differentiation do not actually depend on how the minimum of the energy is found. We don't care what happens in the forward execution. We just care that whatever minimum is obtained allows us to compute then the gradient as the Hessian at the minimum of the energy. And finally, we show that our update rule differs from the implicit differentiation one by just a simple term added to the Hessian, meaning that if one is already using implicit differentiation and is facing instability issues, it might make sense just to add this small correction. So let's move now to some practical experiments. The first thing we'll show is that this simple one-dimensional ransack problem. It's just as a proof of concept, we will randomly generate some points from a normal distribution, mix them with a larger number of outliers, and try to learn the mean of the real values from the normal distribution by minimizing an energy modeled as a sum of radial basis functions. And in this case, the only hyperparameter we want to optimize is the width of these radial basis functions. And what we see is that initially our method and implicit differentiation have similar performances, but then we are meant to draw a series of random values for which the energy is flat enough that the implicit differentiation will face exploding gradient issues, resulting in unbound steps, and it will move to a value of the kernel extremely unrealistic, from which it then has problems recovering, while our method is able, since its updates are dumped, it's able to maintain reasonable values for the kernel size and finally converge to better results. So this is our first result. We then try to apply this to real world data, and we do this moving to the problem of using multiple visual trackers. We consider 72 trackers from the VOT challenge. And the idea is to take the bounding box they predict and to learn how to fuse them together in a better prediction. In this case, we are still using RBFs as a base for our energy, but in this case, we're modeling the upper left and lower right corner of the boxes with the two-dimensional RBFs. And we are learning different values for each tracker, meaning that for each tracker, we are learning 4 kernel widths and importance weight. And what we see in this case is that we start with our training data, we feed it to the trackers, and what we obtain is something that can be interpreted as an energy function, is something that can be interpreted as a density map. And after training, what we see is that we are moving towards something that should be strongly convex, because ideally we want a very high probability, a very high density close to the box corner. But the idea is that while moving from the initial situation to the trained model, we are meant to pass through a configuration in which the energy will be flat enough for implicit differentiation to fail. And we saw this in practice because using two different protocols, we tried to train a model using implicit differentiation and one using Wibergian learning. And what we saw is that implicit differentiation did not allow our model to converge. While using Wibergian learning, we are able to outperform even the best tracker of the challenge or the average of all the tracker's output. So the next step is moving to a different task, human pose estimation. And in this case, what we're doing is we are considering a model that takes two-dimensional poses from 4 points of view and minimizes an energy that's based on the Huber norm of two terms. One makes sure that the pose is, reconstructed pose is compatible with the 2D inputs, while the other makes sure that the reconstructed pose is realistic by using a probabilistic model of the human body. And the idea here is that we are actually not interested just in the output of this energy minimization, because in practice, this problem is solved multiple times for different probabilistic models and different configurations, and then the outputs are fused together. So we are interested in optimizing the final reconstructed pose and not exactly in what happens after each single energy minimization. And in this case, we have a very large number of hyperparameters because the probabilistic model alone has thousands of parameters. And in practice, in the original version of this model, only a small number of hyperparameters were optimized, the one used to fuse the poses and to regulate their scale. And what we decide to do is we try to change how the input poses are produced, how the 2D poses are obtained, moving to a better detector that sadly has a different distribution of the body joints and has one less joint. And what we see is that obviously if we just feed these new poses to our model, we obtain much worse results, because the input poses are not compatible with the probabilistic model, and we would need to retune all the hyperparameters. And using implicit differentiation or Wibergian learning, we can do exactly this. We are able to simultaneously optimize all hyperparameters, and what we obtain are results that are even better than the ones of the original model. And at the time we first submitted this work to NeurIPS over 1 year ago, they were actually state-of-the-art for multi-camera human pose estimation. So in conclusion, we propose an approach that is more robust than implicit differentiation, that can be applied to a strictly larger class of problem. And we have shown how it's easy to move from implicit differentiation to Wibergian learning by adding a small correction. And we have also shown how this is not just a hypothetical problem, but how even for simple practical problems, implicit differentiation can fail. Code for our experiments is available online, and I welcome any question you have at the poster session. Thank you very much for your attention.